Hi everyone, my name is Viraz and I'm a smart contract engineer at Shell Protocol, and today I'm going to be showing you how can we make any DeFi dapp atomically composable. So we're going to talk about what are the current UX issues that exist with the DeFi ecosystem, and then we're going to dive into the code side of things and just dive in how can we explore the solutions that we can implement to sort of solve those UX problems that we have. So to start off, first of all, how many of you guys use DeFi dapps very regularly? Just a raise of hands. Okay, so yeah, this is going to be fun. So this image sort of aptly describes how the current state of DeFi overall looks like right now, where we can see that we still have a bit far in terms of getting to an ideal DeFi UX state. So we're still a bit far off from that, and there's a bit difference in terms of how we speak about it and what do we actually see in terms of UX in different DeFi apps, right? And I mean, the ideal vision would somewhat look like this. Besides, please ignore the approval transaction, which is a forever pain that we have already, which we have. And the second transaction, just focus on that. So that's the ideal UX state for DeFi should look like, where you can do multiple complex operations in just one transaction. For example, you can just let's say if you have wrap BTC, so you can use that and buy an NFT in just one transaction by doing in multiple operations like you see. But the reality is far from this, because the reality is something like this, right? Where you have to do multiple transactions to achieve this, and which involve multiple approvals, switching between different websites, a lot of high gas costs, and of course MEV risk as well, especially with AMM related operations. And we at Shell have sort of been working towards a solution for this, where we have created a set of smart contracts and differentiated the accounting layer and the business logic layer. So you can basically have a track at improving UX that way, where you don't have to put everything inside one contract, and you can break that into two parts and make it more modular. And so you have like two different layers. One is the accounting layer, and then you have the business logic layer. And the accounting layer that we have developed is called the Ocean, which is a ERC 1155 contract, where users can basically interact with that, and the business logic which does all the computation can just be a black box for the users, right? So the idea is that users pass in an array of structs to a smart contract method, which in a protocol definition we call as interactions. So interactions are nothing but sort of batch operations that users can use to do these different primitive related operations. For example, swap, like adding or removing liquidity, etc. Right? And we'll dive more into it as we go along. So this is a short UI snippet that we have from our current dapp, where we have a couple of examples. Where the first example we have is a multi-NFT swap, where you can swap multiple NFTs for USDC in just one transaction, right? And again, this makes it. This shows how composable your dapp can be, where you can minimize user clicks, and do everything complex in just one transaction, right? And so this is one example where you can swap NFT for an ERC20 or vice versa. And the other example we have is an LP to LP swap, right? For example, with different AMMs right now, if you have to migrate your liquidity from one pool to another, you have to do multiple transactions, right? But with Shell, in a way, you can do all of this in just one transaction because of the composable smart contract architecture that I just talked about. So with composability, we have realized that to gain more user and dev adoption equally, you having a composable system gives you power to basically integrate with multiple DeFi protocols without a lot of code complexity, right? And what this does is helps you to create a system where you can, which can be a one-stop shop for DeFi, basically. So a user, for example, a retail user who's is sort of just venturing into Web3, they don't need to know about multiple protocols or how different protocols work. They can just come to one platform and do all their operations there itself, and all the behind the scenes stuff can just be a black box for them, right? And which reduces complexity and sort of simplifies the user experience, and which in turn would help you help us to get more users in Web3 in a way. For DeFi related use cases, right? Uh, so composability is sort of directly proportional to these omni DeFi dapps, where you can, yeah, like I said, just do multiple operations with just one interface, rather than having trouble in terms of switching to different handling different tabs, switching to different websites, etc., and also reduce gas costs a lot, right? Uh, yeah, so to do all of this, to sort of achieve this vision, we have sort of started working and working on this and developed a set of smart contracts called the adapters, which is nothing but a middleware between the shell contracts and any external DeFi contract like Uniswap, Balancer, or Curve. So the idea is that on behind the scenes, the shell contracts communicate with with these adapters, and then these adapters, call these external smart contracts, and hence they are able to compute that result and perform any operation, for example, a swap or a add in liquidity, etc., and then just communicate that back again to the shell contracts, and that's how the cycle works, right? Where there's a two-way communication between the ocean, which is our accounting layer, and the adapter, and then there's a one-way communication between the adapter and the external contracts, and that's how the whole user flow works, which we'll dive into more as we sort of go along, right? Uh, so so this is just a simplified version of the diagram that we spoke about earlier, right? Where there's a user who calls the ocean, right? And there's a method called as compute and do interactions, right? So there's a method in the ocean contract called do interactions, which states in an array of structs, right? And that strut is called as an interaction, right? Like I mentioned earlier. So you pass in an array of different interactions, and interactions can be basically start off. The user flow sort of starts off by first a user locking in their underlying token. It can be an NFT, it can be any ERC20. So they lock in that ERC20 token, and they get in a ERC1155 token in return of the same value, right? And once they do that, then they pass in the second interaction, which is nothing but the business logic based interaction, where they can let's say add liquidity or swap tokens, right? And then at the end, once that's the middle interaction, and the last one would be to unwrap the token. So for example, if I want to swap USDC for USDT, so first I'll wrap USDC. The second interaction will be to swap the USDC, the shell wrapped USDC token with a shell wrapped USDT token, which is again the ERC1155 tokens that I spoke about. And the third interaction would be to unwrap the shell USDC token to the underlying USDC token that you get, right, at the end. So you can basically start off by one token and get the other token back by just in just one click. So that's the whole idea, and I'll dive into the code base now. So you guys can, in case you have your laptops, you can clone this repository, and we can. Anyways, I'll be showing over this presentation. Like I'll dive into the code, and if you want to follow along better, you can clone this repository and just dive in with me. Yeah. Yeah. So I'll just dive into the code now. Yeah. Yeah, I hope this screen is visible to everyone, or should I? I'll probably make it more. Yeah. So the idea is this is what interaction basically looks like, and let me know if you guys need me to show the GitHub link again. So you can basically go to you can search Kauri Labs on GitHub, and you will find a GitHub org link. And the first repository that you see, it's called ETHDenver Adapter Workshop. So you can clone that. This is the link. I'll just keep this link open for a bit so that people can clone the repository if needed. Yeah. So, uh, yeah, so it's called Kauri. The GitHub organization name is called Kauri, and you can just go to that. And the first public repository you'll find would be ETHDenver Adapter Workshop, and you can clone that. And there are like steps in the README where you can first run yarn, and then I'll just probably go over that once. Yeah. So you can clone the repository, and then you can first install all the dependencies with yarn install. And you can just run forge-b to install the Foundry related dependencies. And that's it. And I'll just dive into the code, and we can go over the tests and the code side of things now. Till this point, just wanted to check in with everyone. Till this point, do you guys have anyone has any queries that we should go over before I dive into the code? Because it's a workshop, so I'm just making sure if I should. Okay. Okay, I'll just dive into the code then. Yep. Yeah. So this is the starting point basically where this is the interaction strut that I was sort of speaking about, right? And the first thing we have is a bytes parameter in the strut that we pass into the ocean, which is called interaction type and address. So this is nothing but just an encoded form of the interaction type, which is an enum, and the address of the external business logic contract that you want to interact with, right? Or the ERC20 token in case you want to wrap or unwrap, it's the address of the underlying token that you want to wrap or unwrap. Or in case you want to do a business logic operation, the address here is the business logic contract address, right? Uh, and these are the interaction types that you can use, right? So we have a wrapping of ERC20 tokens, a wrapping of ERC1155 tokens, and 721 tokens, right? So you can the ocean is compatible with all these tokens, token types. So that's the wrap transaction types, and then the unwrap types again are the same. And then there are the compute output amount and compute input amount types, which are basically your business logic related interaction types. So compute output is basically just that you have an input token that you're passing into the ocean, and you'll get a specific amount of output token depending on the value of the token that you're providing, right? And so it's just a buy and sell operation in a way, right? Uh, and now we'll dive into what's the method that we call on the ocean, right? Uh, yeah. I'll need to, yeah, I'll just dive in. Yeah, so this is the smart contract method that any user calls on the UI. For example, if you're interacting with the shell app, which is called do multiple interactions. So as you can see, this takes in an array of interactions of the interaction strut, and then it has IDs, which is just basically the ERC1155 token IDs that we use to compute to keep a track of the accounting for the ERC1155 wrap token balances on the smart contract, right? And then the third part is, of course, the user address that's interacting with the method and which will sort of receive the tokens at the end, right? And then what happens is then this contract will basically call the business logic contract depending on the address that you pass in the interaction type and address bytes parameter that I mentioned, which is this. So we basically decode this the value that you pass into this argument, and based on that, the address that we get, there is a then basically we call the primitive, and the primitive basically then, which is the adapter in this case, and the adapter then basically calls the external contract to communicate and then do that operation that the user wants to do, right? So here is the adapter address that I was talking about, which is this, which is called ocean adapter. It's an abstract contract that different adapters basically inherit. So the idea is that you call in the multiple interaction, the do multiple interaction method on the ocean, and the ocean basically calls the compute output amount method that you see here, right? Where you see three operations basically happening. So the first one is because in order to deposit the underlying token to the external contracts, we'll need to unwrap the token first, because like I said, when you interact with the ocean at the start, you will need to wrap your underlying token into a shell-based, into the shell ERC1155 token, right? So because the token is wrapped, so you'll need to unwrap it first. So this is what we're doing here. We unwrap the token first, and then we call this primitive compute output method, which basically calls the adapter, and calls the adapter specific external contract method, and that this method basically communicates with the external contract to do a particular operation, for example, swapping or adding liquidity, etc. And then you get a result back from this method, which is the output amount, right, basically. And then you basically wrap up the output amount again into the ERC1155 form, right? And that's how you're able to, do basically wrap, you start off by one token and you end up with another. So this is the whole process in terms of interacting with the external contract. Now I'm going to dive into this primitive output method, right? So here is an example which we recently sort of shipped, which is a curve two-pool adapter where we are interacting with a curve pool having two tokens, right? And in this case, in this example, I'll be taking an example of a USDC-USDT pool, right? So yeah, so this is that smart contract method that I was talking about in the previous link, right? This is the method that's been called, and as you see, what happens here is, now the first operation is where we convert the decimals, right? So the idea is that ocean words, when we wrap tokens, the tokens are wrapped into a 18 decimal form, right? And now when you unwrap it, right, we'll need to convert the decimal format into the underlying token decimal. So for example, if you are dealing with USDC, right, and the shell token now, shell version of the USDC token has 18 decimals, but USDC, the underlying token, has only 6 decimals. So you need to convert those values in terms of the decimal of that particular token, right? So this is what happens here. We get the raw input amount, and then what we do is, because an AMM can have 3 operations, right? It can be a swap, it can be a deposit, or a withdrawal. So here we determine what's the compute type, right? And once we do that, we basically, based on the compute type, we call in the curve smart contract methods. So either it can be a swap, or it can be, a user wanting to add liquidity, or like removing their liquidity from the Curve pool, right? So that's how it works. So first we sort of convert the token decimals, then we determine what's the compute type, and then we call the external smart contract method. And at the end, we get the output amount, and then again we convert the decimals back into the ocean-specific decimal amount, which is 18 decimals, right? In case the output token is less than 18 decimals, right? So we convert that back to 18 decimals, and we return this output amount. That's it, right? And then you, like I said, then you just wrap this token, right? So now what I'll do is I'm just gonna I'll walk you guys through a test, right? Just give me a sec. Does anyone has any queries up till this point? And we can go over and I'll move forward accordingly. Okay, no worries. Yeah, so I'll just show you guys how sort of a test looks like in terms of implementing this and testing this in the real environment. So we have these. Yeah. Yeah, so we have these 4 test suites that we have created, right, in terms of testing out these adapters, where we can fork the real environment in this case because our contracts are deployed on Arbitrum. So we use Foundry to fork the Arbitrum network, right, and basically run all these smart contract tests for these adapters. Right, and in this case, like I said, the example that we're taking in is USDC and USDT. Right. So so there are like 3 fuzz-based test scenarios, right? So we start off by a swap, right? Okay, I'll probably have to what this. Okay, yeah. So we start off by a swap test, right? Where we've just taken a Boolean argument in terms of which token that we want to swap and the amount that we want to swap, right? So and based on that, we set the input and the output address accordingly, right? And now I actually had a to-do here because I wanted to for us to sort of code the test scenario, but I can probably just rewrite it and just go over the interactions that way. Yeah, I'll probably do that because not a lot of people have their laptops with them. So probably it will be better for me to just get the code back in and then just go over the test code. Just bear with me for a couple of minutes. Oh, sorry. I'm just doing it for a couple of minutes. I'm just getting the code back in. Shit. Yep. So thanks for bearing with me, guys. Yep. Yeah, so I've added in the missing code that was there, and now we'll just dive into the test, right? So like I said, this is where we start off by sort of creating these interactions and then calling the Ocean smart contract, for example, to swap USDC or USDT for the other token with the help of Curve, right? So the idea is to have a interaction array of 3 items, right? And the first item, like I said, is basically a wrap ERC20 interaction. So where we first wrap the token that we have which is either USDC or USDT, depending on the fuzz input that we get, right? So we do this, and as you see, we have a property here which is called specified amount, where we pass in the amount of the tokens that we want to sort of swap, right? And metadata, we don't need any metadata here because it's just a wrapping operation. So we just do this, right? And then the second interaction is basically the compute interaction, where we compute output amount interaction, where we define the input token that we want to swap and the output token that we want to get, right? And the amount that we want to swap in for, right? So as you can see, here is the compute output interaction that we are passing into this, to the interaction type and address argument that we discussed before. And this is the address of the adapter that I just went over, which is the curve two-pool adapter, right? So basically, we sort of concatenate both these values and then create and get a bytes 32 result, right? Bytes 32 value, which we pass into the strut. And the input token, again, is the shell-wrapped ERC1155 ID. And the output token is, again, the same for the output token address. The specified amount, because the Ocean has a check where if you pass in the maximum amount, it will automatically just take in the amount of the balance that it has, right? That you want to swap in the previous interaction. So it will automatically just take the amount as this amount that we passed in, right? And now the last interaction is to unwrap that token, right? So once you do the swap, the last operation that you'll do is to get the shell-wrapped ERC20 token, burn that, and then get the underlying token back to the user, right? And that's it. And we just call this do a multiple interaction method. And we are able to see that we have a check here in terms of the decreasing and increasing of the input and the output token balances of the user who call this method. And we have these checks that the balances should have increased and decreased. And based on that, we're able to verify that we are able to make these complex operations work in just one transaction, right? And a similar flow is here for deposit interactions as well. The only difference that you'll see is that the output token is basically the output address is basically the curve LP address in this case, because with curve, when you deposit liquidity, you get a LP token back. So this is the address of the LP token that we're using, and we'll be unwrapping the LP token at the end, right? So it's pretty much the same process as in swap. The only difference is the token address that we're using, right? And the other thing is, which is the last part of it is test withdraw, which is again just the withdrawal side of things, where again the difference is that the input token is the LP token, and the output token is is either USDC or USDT, depending again on the fuzz input that we get, right? So we can either, based on that, we have like the test logic in a way, handled in a way where it will adjust the address of the output token. Right, and again, the interaction process, again, it's the same. You have, an array of 3 items, and the input address in this case is the LP token, and the output address is, like I said, is based on the fuzz inputs, right? And again, we check balances at the end, that these balances should be correct, right? And now I'm just gonna run it on my local terminal just to show you guys that how the logs of the transaction look like. Yeah. Yeah. I'll just probably just increase this. Yeah. Yeah, so it's just compiling, and it will run the 3 test scenarios that we just discussed. And it'll show a log, because with Foundry, you just see the test logs, right? It's just taking time to compile. Oh, give me a sec, sorry. Yeah, it's just taking some time to compile, and then once we have it, we'll be able to see the test logs. Yeah, just some warnings, and yeah, it's just running the test. Okay. Let me check this once. Probably have the wrong. Probably debug this once. Yeah, I'll probably debug this, but yeah. Anyways, the idea is to do these operations basically atomically, in that sense that you can do multiple operations, multiple interactions and compute that combine them into one, and and yeah, if and we're looking for more devs to sort of like build on. To sort of build more on build on shell, like create their own adapters which interact with these external DeFi protocols. And our team's gonna be here at the venue throughout the week. So in case you guys have any queries or wanted to discuss any ideas, very happy to discuss that. And we'd love to, yeah, want more people sort of experimenting with the shell contracts. They have been audited recently, released a new version. And we released a new version out there, the V3. And yeah, happy to chat around the contract architecture or any use cases that you're excited about in terms of building for the hackathon or in general. And this is our website. You can scan the code and learn more about it. And yeah, happy to answer any questions. Yep. Thanks. Does anyone have any questions? Thanks, guys.